once again. Hello, everybody. It's my pleasure to give a lecture today in the framework of the seminar series devoted to fractional calculus. And on behalf of all participants of the seminar, first of all, I would like to thank the organizers, Arran and Pavan, for their brilliant idea to establish a series of seminars devoted to fractional calculus. I am sure that this series will be very useful for the whole fractional calculus community and especially for the newcomers and young researchers. So the title of my today's presentation is the General Fractional Calculus Operators with the Sonin kernels, basic properties, applications, and history of origins. I will start with the history of origins and with some results obtained by Abel and Sonin, and then proceed with the recent history of this topic with the emergence of general fractional integrals and derivatives, and then consider a special class of this fractional of these objects, namely general fractional integrals and derivatives with the Sonin kernels from a special class of kernels that I will introduce later. And as an application of this theory, I would like to show you the so-called generalized convolution Taylor formula and the generalized convolution Taylor series. And then I provide some references and further a short overview of further results. The story with this subject, with the general fractional calculus, began about 200 years ago with publication of two papers by Abel devoted to the so-called generalized totachron problem, where he formulated a model, an analytical model of this problem and solved it. The first paper by Abel was published in Norwegian language and the second one in German language. So that probably it was the reason, one of the reasons that the papers were not well recognized. In the recent publication by Podlubny, Magin and Trimarush, they provided English translation of this very interesting, important papers by Abel. And I would recommend those of you who cannot understand German or Norwegian language to read the paper by Podlubny. So the totachron problem was a classical problem solved already a long time before publication of the papers by Abel. For example, in the works by Christian Huygens, who showed with some advanced geometrical methods that the totachron is a suitable part of the cycloid. And the totachron is a curve that possesses the following property. If you put a mass point on this curve, then the sliding time of the mass point to the end point B doesn't depend on the initial position of the mass point. So it's just a mechanical problem. Of course, it's supposed that the friction, that there is no friction in the system, and the movement is forced by the uniform gravity. Well, starting from the energy conservation law, Abel derived the formula for the sliding time that along the curve that is described by the curve phi of S. And in fact, in his publications, Abel considered it a more general problem. So he supposed that the sliding time does depend on the initial position. So we have not just the constant time t, but a function t of h, where h is the initial position. In fact, Abel also considered a mathematical generalization of this physical problem he replaced the square root in the kernel of this integral by the arbitrary power law function with the order alpha between 0 and 1. As you can see, the formula that Abel derived for the sliding time is nothing else than the object that is nowadays referred to as the Caputo fractional derivative. So Abel looked for inverse operator to the Caputo fractional derivative, and under the condition phi of 0 is equal to 0, and this condition follows from his model, he derived the solution formula in terms of the integral operator that is nowadays called the Riemann-Liouville fractional integral. So both these objects were introduced already by Abel. And to derive the solution formula, Abel employed the connection between the kernels of these both operators. These are power law kernels. And in fact, he used the fact that the Laplace convolution of the power law function tau to the power minus alpha and the power law function tau to the power alpha minus 1 is a constant. This is a constant in the form pi divided by sine of alpha pi, and it's really the constant that appeared in Abel's solution formula. We know that this constant is nothing else as the product of gamma of alpha and gamma of 1 minus alpha. Well, if you think about the modern form of the Abel integral equation, then in the literature, the Abel integral equation is normally written in this form. So it's the so-called Riemann-Liouville integral, but it was already introduced by Abel. And the solution formula is provided in form of the Riemann-Liouville fractional derivative. But in the original publications by Abel, his equation looked like this. Yeah, his equation was in form of the Caputo fractional derivative, and the solution to this equation was derived by him in form of the integral operator that is nowadays referred to as the Riemann-Liouville fractional integral. So you see that the modern form of the Abel integral equation and its solution is not exactly the same as the equation and solution that was derived in the publications by Abel. But of course, they are connected. Well, then the next step in this story was done about 60 years later, after publications of Abel by Russian mathematician Sonin. And Sonin recognized that the main component of the Abel solution to his integral equation was this formula that you see at the bottom of the slide. So the convolution of two power law functions that I will denote by h alpha and h1 minus alpha. H alpha is a power law function divided by the gamma function of alpha, the last line of this slide. And Sonin said, well, let's insert instead of power law functions two arbitrary functions, not arbitrary, but two functions, kappa and k, with the property that their convolution is equal to 1. And then the Abel solution method works exactly in the same manner for these kernels. This condition, the kernels that satisfy this condition are referred to nowadays as the Sonin kernels, and the condition is referred to as the Sonin condition. And then if we take two functions that satisfy the Sonin condition, then following the method by Abel, one can easily solve this integral equation with the kernel kappa. And the right-hand side of this equation is referred to nowadays as the general fractional integral with the kernel kappa. And its solution, it's very easy to derive this solution, no problem, has the form that is nowadays referred to as the general fractional derivative. It's first-order derivative applied to the convolution of K and F, and K is the Sonin kernel associated to the kernel kappa. Well, of course, Sonin did not introduce this notation, general fractional integral or derivatives, and he derives the solution formula also formally without specifying any spaces of functions and without providing conditions for validity of his derivations. So in a certain sense, it was the prehistory of the general fractional calculus. And here on this slide, I provide some examples of the important Sonin kernels. Of course, the power law kernels, H alpha and H1 minus alpha, that were introduced by Abel. Then the kernels in terms of the Bessel function, G alpha minus 1, and the modified Bessel function I minus alpha. This pair of the Sonin kernels was derived by Sonin. Then also very interesting pair, the sum of two power law functions, and the associated kernel K is given in terms of the Mehta function. This pair was first introduced in a publication by Andrzej Haniga. And nowadays, a lot of attention in fractional calculus is given to this pair of the Sonin kernels in terms of the so-called three parameters Mehta function or the Prabhakar function. There are many publications devoted to the integral and differential operators with these kernels. And it's really a very important example of the Sonin kernels, because under certain conditions, these kernels are completely monotonic functions. That is very important for applications. Further examples of the Sonin kernels can be found in the publication by Samko and Cardozo and in my recent preprint. Well, what we spoke about, as I already said, can be characterized as a prehistory of the general fractional calculus, and the real history or the birth of the general fractional calculus operators with the Sonin kernels was a publication of a paper by Anatoly Kochubey, General Fractional Calculus, Evolution Equations, and Renewal Processes in 2011. In this paper, for the first time, these operators were called the general fractional calculus operators, and Anatoly also introduced a special, very important class of the Sonin kernels that is nowadays referred to as the Kochubey class of the Sonin kernels. He characterized this class in terms of the Laplace transform of one of the kernels, K. So the Laplace transform should exist on the real positive axis, and it should be a Stieltjes function, and then some asymptotical behavior is required. Of course, especially the second condition was very important in this theory by Anatoly, but still it's a heavy condition and not so easy to prove, to verify for concrete functions. And in this publication, Anatoly also introduced the so-called general fractional derivative in the Caputo sense, or the regularized general fractional derivative. You see here that the function, that regularized general fractional derivative is the general fractional derivative applied to a function regularized at the point 0, that can be represented as fractional integrals of the derivative of the function f for some functions from certain classes. And among other matters, Anatoly derived the following results. He proves the first fundamental theorem of fractional calculus. That means that the fractional derivative is left inverse operator to the fractional integral. Then he considered two basic equations, very important for applications. First of all, the fractional relaxation equation with the regularized generalized fractional derivative, and proves that its solution to the solution to the corresponding Cauchy problem is completely monotone. And then he considered the Cauchy problem for the general time fractional diffusion equation with this derivative, and derived a very important result that its fundamental solution should be is a spatial probability density function evolving in time. So with these results, the operators that Anatoly introduced would be really called generalized fractional calculus operators. Surprisingly, this important paper by Anatoly remained unrecognized, mostly unrecognized by the fractional calculus community for many years. And the next publication devoted to this subject appeared in 2016. It was the publication General Time Fractional Diffusion Equation, Some Uniqueness and Existence Results for the Initial Boundary Value Problems, where initial boundary value problems on the bounded domains for the general time fractional diffusion equation were introduced and treated. And this equation were time fractional equation with the regularized general fractional derivatives. Among other things, in the paper, some estimates of the general fractional derivative at the maximum points of the functions were derived. And based on these estimates, the maximum principle for this initial boundary value problems was derived. And then, of course, other results like uniqueness of solutions, some a priori norm estimates, and also existence of solutions. However, in this publication, the kernels of the general fractional derivatives and integrals were not exactly from the Cauchy class. So we post here in this publication with Masahiro slightly weaker conditions on the kernels of the fractional integrals and derivatives compared to the ones posed by Anatoly. And here I would like to make an important remark, namely that there is no unique general fractional calculus. In fact, there are many different kinds of general fractional calculus or just fractional calculus, and the essential components of any general fractional calculus, they are as follows. So first of all, one should specify a Sonin kernel or a subset of the Sonin kernels you work with. And then, of course, this operator should be considered on some suitable spaces of functions. Yeah? And then once you fixed both of these components, you can develop a new theory, a new general fractional calculus theory. And some examples are as follows. For example, we take the classical Riemann-Liouville fractional integrals and derivatives with the Sonin kernels H alpha and H1 minus alpha on the LP spaces or Hölder spaces H alpha, H lambda, and you get a fractional calculus. Or you can take the Sonin kernels in form of the Prabhakar functions and consider the general fractional derivatives on the space C minus 1 that I will introduce on the next slide. So you get a different kind of theory. Or you can consider the general fractional integrals and fractional derivative with the Kochubey kernels on the class of absolute continuous functions, and then you come to the theory developed by Kochubey. So in my today's talk, I will focus on another kind of a general fractional calculus, namely a general fractional calculus with the operators, with the Sonin kernels that belongs to the class C-1. As you see, these are Sonin kernels that belong to a special space of functions C-1, 0, and the class C-1, 0 consists of functions in the form power law function multiplied with a continuous function, and the exponent p is between -1 and 0. It means that the kernels from this class they possess integral singularities of the power law type at the origin. Please note that not all Sonin kernels can be expressed in this form. So there are other classes of Sonin kernels with other types of singularities. For example, of power logarithmic type, singularities of power logarithmic type. And today we construct a theory, general fractional calculus theory on the space of function C-1 and its subspaces. And this space is very convenient for dealing with fractional integrals and derivatives, because you know that even if you deal with the classical Riemann-Liouville fractional integrals and derivatives, then typically you have their power law singularities in the kernels, in the solutions to the differential equations. And the elements of the space C-1, they have or can have a power law singularity. So they are represented in the form t to the power p multiplied with a continuous function f1. Initially, this space of functions and more general spaces of functions were introduced by Dymowski in the framework of his operational calculus for the hyper-Bessel differential operator. Well, on this slide, I listed the general fractional integrals and general fractional derivatives. They have exactly the same form as the form that was derived already by Sonin, without calling them general fractional integrals and derivatives, and then by Anatoly Kochubey. So we have exactly same operators, the general fractional integral as Laplace convolution operator, and then the general fractional derivative in this form, and the regularized general fractional derivative that was introduced by Anatoly Kochubey. So the form is the same, and the difference is in the class of the kernels. So we consider now these operators with the kernels, Sonin kernels from the class S-1, and on the special spaces of functions S-1 and its subspaces. Well, we start with the basic properties of the general fractional integrals with the kernels from the class C-1. Mapping property, so the integral maps C1 into C1. So commutativity law is of course valid because the Laplace convolution is commutative. Then we have the index law in this form. You see that the result of composition of two fractional integrals is a fractional integral with the kernel that is equal to convolution of the kernels kappa 1 and kappa 2. It's a general form of the index law. And if we project this form to the Riemann-Liouville fractional integrals, then of course this index law takes the very known form because we know that the convolution of H alpha and H beta is nothing else as H alpha plus beta, and then we get immediately this special case of the index law for the Riemann-Liouville fractional integrals. Well, before proceeding with the properties of the general fractional derivatives, I would like to introduce a generalization of these objects, and then we formulate the basic properties already for this generalization. Namely, first we introduce the n-fold general fractional integral. It's very clear how to introduce it. This object is just a composition of n operators of n general fractional integrals. And again, we use the index law for the general fractional integrals, and we can represent this n-fold general fractional integral as one-fold integral, where kappa to the power n is not a power law function, but it's a convolutional power. So kappa to the power n in square brackets is nothing else as n times convolution of the function kappa. Please note that this operator at the right-hand side of this equation is not necessarily a general fractional integral. Why? Because the kernel kappa, the convolutional kernel kappa to the power n is not always a Sonin kernel. It could be a Sonin kernel, but sometimes no. So in effect, it's a new object, the n-fold general fractional integral, that is not necessarily reduced to the general fractional integral. Then we introduce the n-fold sequential general fractional derivatives. In the Riemann-Liouville type, is just a composition of n general fractional derivatives of the Riemann-Liouville type, and the n-fold sequential regularized general fractional derivative is a composition of n general regularized fractional derivatives. These definitions are quite natural, nothing new. And then we consider now some properties of the n-fold general fractional integrals and n-fold sequential general fractional derivatives. In particular, maybe one of the most important properties that is also expected somehow is that the general fractional derivatives, both of Riemann-Liouville type and regular derivative as is an element of the space of the functions where this property is valid is more narrow compared to the space C minus 1. This functional space consists of all functions that are images of the space C minus 1 with respect to the fractional integral with the kernel K. So this the definition of the space is here. But similar things are also valid, of course, for even for the classical Riemann-Liouville fractional derivative and integral, and Caputo fractional derivative and the Riemann-Liouville fractional integral. Well, the proof of all these results, the proofs, they are more or less technical. So I omit the proofs, and you can find the proofs in my publications. I will, at the end of the lecture, I will present you some literature overview, and you can find there all details. Well, the second important result was proving the so-called second fundamental theorem of fractional calculus for the sequential general fractional derivatives. for the functions from the special space C-1 Kn, and this space you can see at the bottom of the slide is also a quite general, quite natural. So it consists of all functions from the space C-1 with the property that the g-fold sequential general fractional derivatives of the function f also belong to the same space C-1. So it's this space is more or less a straightforward analogy to the space of n times continuously differentiable functions, in fact, yeah. And if we take a function from this space, then the composition of the n-fold fractional general fractional integral and the n-fold general fractional derivative can take the following form. We have here the function f of t, but we have here also some corrections in form of a convolution polynomial, in fact, yeah. You can see here that we have here some coefficients in the sum, and this coefficients depend on the function f and are provided with evaluation of some compositions of the operators of the function f at the point 0, and then we have convolutional powers. So this this sum can be considered as a kind of convolutional polynomial. So the derivation of this formula is also more or less technical, straightforward. You can find it in my publications. But then let's determine the function f of t from this equation. So if we add the sum of this convolutional polynomial to the both sides equation, then we get formula for the function in terms of the polynomial plus
I guess we lost Professor Luchko, so I'll just quickly contact him and try to get him back online.
So can you hear me now?
Yes, Professor,
Yes.
we can hear you now.
Yeah. Should I return to last slide?
Yes, yes, please. That
But
would
we
be
cannot
nice.
see your screen now. You need to share again.
Yeah, okay. Sorry, my internet connection is probably not very stable. As I already said, I'm not in Berlin now, but in my garden. So can you see now?
Yes, we can see now the screen.
So should I return to the previous slide?
Yeah, that would be nice actually. So we could
I
have
spoke about the so-called second fundamental theorem for the sequential general fractional derivatives. The formula looks like this. So if we construct a composition of the n-fold general fractional integral and the n-fold sequential general fractional derivative, then we get the function f corrected by some additional terms in form of a convolutional polynomial. Yeah? In fact, what we have here in the sum are some coefficients, some numbers multiplied with convolutional powers. So it's a kind of convolutional polynomial. And if we solve this equation for the function f, then we get nothing else as a generalization of the Taylor formula. So And this generalization, I call this formula the generalized convolution Taylor formula, and it looks like this. So for the function from the space C-1 Kn we introduced earlier, so it's an analogy to the space of the n-fold differentiable functions, in fact. So we have the following representation of this function f in terms of the convolution polynomial plus a remainder. And the coefficients in these convolutional polynomials are provided in terms of the general fractional integrals and derivatives. You see here that we have here a special composition of these operators applied to the function f and evaluated at the point 0. And the remainder in the generalized convolution Taylor formula can be represented immediately as this operator, and then we can apply the integral middle value theorem to the general fractional integral and get a formula for the remainder that is a generalization of the Lagrange formula for the remainder in the classical Taylor formula. So we have here, we evaluate this n-fold general fractional derivative of the function f at a point tau that is located between 0 and t, and then we multiply this value with a certain function, yes, a certain basic function. So as you see, we have here more or less a generalization of the Taylor formula, a far-reaching generalization. And if we specify this formula for the case of the Sonin kernel H alpha, this means for the case of the Riemann-Liouville derivative, then we get this nice formula, representation of the function f in form of a power law polynomial, with fractional exponents. And you see here that this polynomial is singular at the point 0. So it belongs to the space C-1, but it's not continuous. And the remainder in this formula is expressed in terms of a composition of the Riemann-Liouville fractional integral and the sequential Riemann-Liouville fractional derivatives. So this formula is or was already known in the fractional calculus. It was derived by Jvashan and Nersesyan in one of their publications in more or less same form. And the remainder can be also represented in terms of the in a kind of the Lagrange formula for the remainder in the Taylor formula. So it's n-fold Riemann-Liouville fractional derivative of the function f evaluated at the point tau, and tau is between 0 and t, multiplied by this power law function. And if we let in this formula alpha going to 1, then we get the normal Taylor formula. Well, we derived already the Taylor formula, and of course the natural question would be if it would be possible to derive a generalization of the Taylor series. Yeah? And indeed it's possible, and in connection to this question, the so-called convolution series, they play a very essential role. The convolution series are a kind of generalization of power law series. So if we take a function from the space C-1, and if we take a power law series with non-zero convergent radius, and if we substitute instead of powers the convolutional powers, then we get the so-called convolution series, and this series is convergent for all t greater than 0, and the sum belongs to the space C minus 1. So this was proved in one of my publications, and the convolution series are very interesting, in fact, new objects, new form of special functions. And if we, for example, if we start with the geometric series, for example, and substitute instead of powers, convolutional powers, then we get a very important function that belongs to the space C minus 1. And as expected, this function plays a very important role in solving fractional differential equations with the general fractional derivatives. This is also a very important topic, but today I have no time to go into details. And if we consider some examples of this convolution series, for example, with the Sonin kernel kappa is equal to 1, then we can calculate, of course, the convolutional powers of this function kappa, and they are also power law functions. And if we substitute this result in the formula for the convolutional series, then we get the series for the exponential function. Yeah? The same procedure can be done for the kernel H alpha of the Riemann-Liouville fractional integral. So we can calculate here the convolutional powers also in explicit form. And if we substitute this form into the formula for the convolution series, then we get the Mehta-Kleffler function with two parameters and with a power law weight. Yeah, and we all know that this function is very important in the theory of the fractional differential equations with the Riemann-Liouville fractional derivatives. Well, now we consider the following question. Let's take a function f that is represented as a sum of the convolution series. The series is convergent if we suppose that the kernel kappa is from the space C minus 1 and the corresponding power law series is convergent, then we have here the sum is a function from the space C minus 1. And the problem is how to determine the coefficients in this convolution series. Of course, we already, in fact, solved this problem because we derived the convolutional Taylor formula. And the convolutional Taylor formula is nothing else as a partial sum of this infinite series. And if we follow this line, then we get a very nice formula for representation of a function f from a certain class of functions in form of convolution series with respect to the kernel kappa. You see here that kappa is in fact any kernel from the class C minus 1. And here we have convolutional powers instead of power law functions, and the coefficients of this series are expressed in terms of the general fractional integrals and derivatives of the function f evaluated at the point 0. Well, what I showed you were the results obtained for the general fractional derivatives of the Riemann-Liouville type. And this analogy, similar results were also obtained for the case of the sequential regularized general fractional derivatives or the generalized fractional derivatives of the Caputo type. And as expected, the formulas in this case are very different from the ones we already looked at. And it's not a surprise because even in the case of the Riemann-Liouville fractional derivative and Caputo fractional derivative, many formulas are very different. For example, the generalized convolution Taylor formula for the regularized general fractional derivative looks like this. You see here that we still have a kind of a convolutional polynomial, but this polynomial is not singular and the coefficients are different and also the basis functions are different. And of course, the formula for the remainder is very different. If we specify this formula for the case of the Sonin kernel H alpha, it means for the kernel of the Riemann-Liouville fractional integral, so we get a generalized convolution Taylor formula for the Caputo derivative, and this formula looks like this. Yeah, you see here that the corresponding polynomial with fractional exponents is continuous. It's not singular anymore, as in the case of the general fractional derivative, but it's continuous, and it was, of course, expected. Yeah. And the remainder, in this case, the remainder in this generalized convolution Taylor formula is expressed also in terms of the Riemann-Liouville fractional integral and the sequential Caputo fractional derivatives. This result is more or less new. I didn't see any publications devoted to this Taylor formula for the Caputo derivative, but it's just a very special case of the general formula. Well, you see here that the results obtained for the Riemann-Liouville fractional derivative and the Caputo general fractional derivative are different, but there is a possibility to unify both of these results. How to do it? If we come back to the classical Riemann-Liouville fractional derivative and Caputo fractional derivative, then all of you are for sure aware of a generalization of this derivative, of the so-called Hilfer fractional derivative, that combines both definitions. So the Hilfer fractional derivative is defined as a composition of three operators: first fractional Riemann-Liouville integral, first order derivative, and then another Riemann-Liouville fractional integral. And for special cases of the parameter beta, we get here both the Riemann-Liouville fractional derivative and the Caputo fractional derivative. And nowadays, there are many publications devoted to the Hilfer fractional derivative or to the fractional differential equations with the Hilfer fractional derivatives. And this publication automatically cover both Riemann-Liouville fractional derivatives and Caputo fractional derivatives. Well, for the general fractional derivatives, one can introduce a very similar generalization, and it was already done. So first of all, we need now three kernels, and these three kernels, kappa, k1, and k2, that I call the first level kernels of the general fractional derivatives, they should satisfy a property that is similar to the Sonin condition. So the Laplace convolution of all three functions should be equal to 1. One typical example of these kernels are the kernels, power law kernels, H alpha, H gamma, and H1 minus alpha minus gamma. And if we consider these kernels, then we will get the Hilfer fractional derivatives. So we will see it on the next slide. So these three functions, they satisfy this condition that is written down on the top of this slide. Also in this case, to proceed with the theory, we have to specify a class of the Sonin kernels. And I suppose in what follows that all the functions kappa, k1, and k2, they are from the space C minus 1, and the set of such kernels will be denoted by L11. First level kernels of the general fractional derivatives of the order less than 1. Oh, and now with these kernels, we can define an operator that is an analogy to the Hilfer fractional derivative. So I call this operator the first level general derivative, and it's a composition of two general fractional integrals with the kernels k1 and k2, and the first order fractional derivative. And also in this case, this object, the first level general fractional derivative, covers both the general fractional derivative of the Riemann-Liouville type and the regularized general fractional derivative. One can define also, of course, such objects of arbitrary order. One can define these objects with the composition of several fractional integrals and several first order derivatives that could be called, or that are called nth level general fractional derivatives. In fact, these objects are a far-reaching generalization of the operators that are called Jbashan-Nersessian fractional derivatives. By the Jbashan-Nersessian fractional derivatives, they considered similar compositions, but with the Riemann-Liouville fractional integrals with special orders. And now we can extend this definition to more general operators. Well, of course, many other results regarding the general fractional integrals and derivatives and fractional differential equations with these objects were already obtained, but it's not possible to speak about all of these results in one lecture. Maybe one day the organizers of the seminar provide me with opportunity to give an additional lecture. But now I would say that we introduced already the basic definitions, the basic ideas, and operators and basic results. But finally, I have still 5 minutes, as I see. I have some time to give a short survey of other results and related publications, and provide you with the important references. As I already said, the history of origins of this topic was made in these 2 publications by Abel, and please look at the English translations of these publications in the paper by Podlubny, Magin, and Trimarush. And of course, the next step was the paper by Sonin, but still it was a prehistory of this topic. And the real history, as I already said, began with the paper by Anatoly Kochubey, published in 2011, and then in the chapter General Fractional Calculus, published in the Handbook of Fractional Calculus with applications. Anatoly provided a more extended version of this theory. And in the paper, General Time Fractional Diffusion Equation, some uniqueness and existence results for the initial boundary value problems, the initial boundary value problems for the general diffusion equation with the general fractional derivatives was considered for the first time. And then in a series of my publications started from the year 2021, I introduced this operators with the Sonin kernels from the class S1, and also extended the theory to the case of the arbitrary order general fractional integrals and derivatives. Please take into consideration that the definitions that I showed you today of the general fractional integrals and derivatives, they can be interpreted as the fractional integrals and derivatives of the order between 0 and 1 in a certain sense. Yeah, but they can be extended to the case of arbitrary order and to the case of sequential operators and so on. In this paper by Tarasov, he used the general fractional integrals and derivatives introduced before to develop the so-called general fractional vector calculus. And in this paper, the first level general fractional derivatives were introduced for the first time. I showed you the definition of these derivatives today. Then the general fractional integrals and derivatives on a finite interval were also introduced already and investigated, because the theory that I presented you today is valid for the function defined on the real semi-axis. So for the finite interval, you have adjust some definitions and some theory. Then the general fractional calculus operators of distributed order were already introduced, multidimensional case, Riesz form of the general fractional derivatives was already considered, and so on and so on. And it's important to mention that the theory of general fractional integrals and derivatives already found its first applications, especially in a series of papers by Vasily Tarasov. He used this mathematical theory to suggest some non-local physical theories like fractional dynamics, quantum dynamics, electrodynamics, then non-local statistical mechanics, non-local classical theory of gravity, and so on and so on. Of course, it's difficult to say. I am not a physicist, and difficult to say if these theories have some sense, but Vasily Tarasov mentioned some potential applications and some arguments for his theory, so I suppose that they have some sense. However, some applications for sure have sense, namely applications of this theory in the linear viscoelasticity and to the anomalous diffusion theory. So in the publications that are listed on this page by Atanaskovich, Pilipovich, Bashlyakova, Gorska, Hartzela, and so on, the general fractional calculus, integrals and derivatives were applied to suggest some advanced models in the linear viscoelasticity and in the anomalous diffusion. And the author of these publications also provided some arguments for validity of the model. So I hope that it's really useful. This theory is really useful for applications. Still, the theory of the general fractional integrals and derivatives is more or less young theory. Of course, it has origins in the publications that were done by Abel already 200 years ago, but only recently one started to seriously deal with this theory, with applications of this theory, and there are still many open questions. And then I invite all of you who are looking for new topics for research to join research in this area. So my time is over, and then I thank all of you for your attention, and questions and comments are very welcome.
Thanks, Professor Luchko, for the nice talk. I see Professor Kolokso has raised his hand. So can you please unmute yourself and ask the question?
Yes, please. Thank you very much for a very nice talk. I have very small, possibly stupid question, but it somehow disturbs me. You call this Sonin pair. This is very nice theory, but after all, this is general integral operator and its inverse. So how you say, what is really fractional in this theory?
It's a good question, in fact, and in my opinion, the answer was given in the paper by Anatoly Kochubey. Yeah, so in his paper, as I already mentioned, he introduced this general integrals, these operators, general fractional integrals and derivatives, and considered the relaxation equation with this operator and the Cauchy problem with the Laplace operator in space and with the time general fractional derivative. And in this case, in both of these cases, he derived properties of solutions to this equations that are analogous to the properties of the corresponding equations with the first order derivatives or with the Riemann-Liouville fractional derivative. And in my opinion, it's a very strong argument for calling these operators general fractional integrals and derivatives. But I mean, of course, in a sense, you have it's well, it's not there is not answer that is 100% true. Yeah, I mean, it's just an interpretation. So these operators can be considered as a far-reaching generalization of the conventional fractional operators like the Riemann-Liouville fractional integral, Riemann-Liouville fractional derivative, and Caputo fractional derivative. Yeah, and it's a motivation for calling them the general fractional operators. Of course, in a certain sense, these operators could be also called Sonin integral and differential operators. Why not? Yeah, could be also possible. But in fact, your question should be addressed to Anatoly Kochubey, who introduced this theory and called these operators for the first time general fractional integrals and general fractional derivatives. And this name was okay with me, so I continued to use it just, yeah.
I agree with your explanation. And I would like to thank you for developing this approach.
I don't see any more raised hands. So if there are any, okay, I see one, Elena.
Thank you very much, Professor Luchko, for the interesting talk. I probably have only one question, not probably hard, but do you know when it is necessary to use fractional Taylor series in some practical application, etc.? Why we need to use fractional Taylor series?
Well, I am not aware of any concrete applications. Of course, the normal Taylor formula can be interpreted as approximation of more or less arbitrary functions by polynomials. Yeah, and polynomials are very simple objects. So here we have a kind of a parallel to the Taylor formula, but the representation is different. Yeah, you see here that we have a representation of more or less arbitrary function. Of course, not completely arbitrary. Some conditions should be posed as a so-called convolution polynomial. And convolution polynomials, they are also basic objects in the framework of this theory of the general fractional integrals and derivatives. And using concrete functions, so we can substitute here, in fact, any Sonin kernel and get potentially useful representations. For example, in the case of the kernel H alpha, we get here representation of a function from a special class in terms of polynomials with fractional exponents, and these polynomials are even singular at their origin. So I can imagine that this formula could be useful, but it is potentially, for example, for numerical methods for equations with fractional derivatives, or for other problems that are solved in classical analysis by polynomials. Yeah.
I see. Thank you very much.
For example,
me-
continue another argument. In one of my papers, for example, I employed the convolutional series to derive solutions to the fractional differential equations with the general fractional derivatives. I mean, we know that classical Taylor series can be, or power law series can be used to derive some solution formulas for the linear differential equations with the integer order derivatives, even with nonlinear coefficients. For example, Bessel equation, you can derive solution in form of the series by just substituting the power law series and by determination of coefficients. And in the case of the fractional differential equations with the general fractional derivatives, you can use exactly the same method, but instead of power law functions, you have to use more general objects, this convolution series and Taylor series. It's, for example, one of the applications of these objects.
I see. Thank you.
I don't quite see any more raised hands. So if there is any question, you can unmute your mic and ask the question. Okay, Professor, I have one question. So I was looking into your other paper where you introduced modified Sonin conditions. To extend it to arbitrary order. So my question here was that if there is a class of kernel functions where n is equal to 2 in that modified Sonin condition, and let's say n equal to 1, another class of functions, will this so for example, this n equal to 2 will also belong to the class, it's to the same class of functions, or not, or the intersection between these two set of is a null set, or there is a continuous inclusion.
Yeah. So thank you for the question. In fact, the Sonin condition plays a very important role here in the whole theory, and this one can be interpreted as the power law function h1. And in a certain sense, this one at the right-hand side of the Sonin condition says that the generalized order of these operators, general fractional integral and derivative, they are between 0 and 1. So this one is nothing else as a condition for restriction of the order. And in the case of the classical, for example, Riemann-Liouville fractional integrals and derivatives, everybody knows that they can be defined for arbitrary order. But if we apply this theory for the kernels of the Riemann-Liouville fractional integral and derivative, then you see here that the kernels, they satisfy this condition only if alpha is between 0 and 1. It means that applying this theory to the power law kernels, we get just the Riemann-Liouville fractional integrals and derivatives of the order between 0 and 1. And to extend this theory to the arbitrary orders, we have to extend the Sonin condition. We have to change the Sonin condition, and instead of 1, we can put there arbitrary convolutional power of 1 to the convolutional power n. And this would correspond to the n order derivative, in fact, yeah. And then we can develop a theory analogous to the theory of the Riemann-Liouville fractional derivatives and integrals of arbitrary order. Of course, even in this case, we have to fix the class of the Sonin kernels that satisfies this generalized Sonin condition. and I have done this in my publications. So we can, for example, consider still functions, Sonin kernels that belong to the space C-1, yeah, and satisfy this generalized condition, Sonin condition, and then we can extend this theory to the operators of arbitrary order.
So the part I was trying to understand here is, like, for example, take n equal to 2 and n equal to 1. Can there be an example where the kernel belongs to both of them or no?
Well, you mean that some kernels simultaneously satisfy the Sonin condition and the generalized Sonin condition?
Yes.
Of course not, because you have here different right-hand sides. So it means if you change the 1 to the convolutional power, 1 to the convolutional power 2, for example, then of course you change this condition, and the classical Sonin kernels, they will not satisfy this condition automatically.
Okay.
Yeah.
Thank you, Professor. Are there any more questions or comments? Okay, no. So we close the talk here. Thank you very much, Professor Luchko, for the very nice talk. The next talk will be by Professor Mainardi on the coming Friday, same time. I'll send out the Zoom link on Monday. Thank you.
So thank you again for participation, for organization of the seminar, and it was my pleasure to give a talk here, and hopefully see you next week again. Thank you.
Looking forward to it. Looking forward to it.
Yeah.
Thank you.
Bye.
Thank you. Bye.
See you. Bye.
See you.
See you.
Bye.
Thank you very much.
Thank you.
Thank you.